Jain to all. Today I am here to present the video lecture on subject control system BEC602, and this is the third lecture of the series. And today I am including interesting topic root locus, which is a method for finding out the stability in the time domain. So we have given the open loop transfer function of the system, and from that open loop transfer function of the system, we have to find out the closed loop stability of the system. And with the help of root locus, we can also find out that the relative stability of the system. Means when we are varying some parameter, generally the parameter that we are going to vary is the gain, is the open loop gain. So by changing the open loop gain, how your system will become stable to unstable. So let us start. And so root locus introduction. So stability of any closed loop system depends on the location of roots of the characteristic equation. That is the location of the closed loop pole. So you know the roots of characteristic equation are nothing but the closed loop poles of any transfer function. So it is advantageous. To know how the closed loop poles move in the S-plane if some parameter of the system are varying. So we have given the system function and open loop transfer function. And what we will do, we will change some parameter, and as we will change the parameter, then based on that changed parameter, the location of the poles will be changed. Means you can say, as we will continuously change the parameter, then continuously poles will change their location, and the parameter that we are going to choose is the gain, open loop gain. So the knowledge of such movement of the closed loop poles with small changes in the parameters of the system greatly helps in the design of any closed loop system. Such movement of the poles can be known by the root locus method introduced by W.R. Evans in 1948. So basically, when we change the parameter, which is open loop pole of an system, then the roots will start moving, and this movement of roots is first noted by W.R. Evans, and hence it is known as this root locus method. So if you will see, this is a graphical method in which movement of poles in the S-plane is sketched when a particular parameter of system is varied from 0 to infinity. So what we will do, we will change the parameter from 0 to infinity. Note that the parameter is usually the gain, but any other parameter may be varied. But for root locus method, gain is assumed to be a parameter which is to be varied from 0 to infinity. So it means we will take the open loop gain k as a parameter to obtain the root locus. Locus means simply when you will change the open loop gain k, so all the roots of the characteristic equation will start moving, and we have to sketch the movement of the roots, and that is basically your root locus. Okay, so let us start with a simple problem wherein we can see that what is this root locus. So let us take an example. Consider unity feedback system with GS equals to K by S. It means you can say whenever we are writing unity feedback system, it means HS equals to 1. Obtain its root locus. So how can we do this? First of all, we will write the characteristic equation, and characteristic equation is nothing but 1 plus GS into HS equals to 0. Here HS equals to 1 and GS is K by S. So you can say 1 plus K by S equals to 0, or you can say S plus K equals to 0. So you can see here S plus K equals to 0. Now the root of this equation is located at S equals to minus K. So from here you will get the relation S equals to minus K. Now if you will change the gain K, then the value of S will become changed. So you can see this equation is a first order equation. So only one root is there, and that root is basically S equals to minus K. So what we are doing, now we will vary the gain K from 0 to plus infinity. The location of this root is going to change, and the locus obtained by joining all such locations when K is varied from 0 plus infinity is called the root locus. Okay, so root locus is the locus of the movement of this root s equals to minus k. So first we will check the value at k equals to 0. So we will get s equals to 0 according to this equation. Then at k equals to 1, it will become minus 1. At k equals to 10, it will become minus 10, and up to so in plus infinity. When you will check it at plus infinity, you will get the value will become minus infinity. Now these are the values. Now we will plot it on S plane. So you can say this is the S plane, and this is the point where gain k equals to 0, and the location is s equals to 0. And as soon as you have increased the value of gain by 1, you can say s will become minus 1, means we will get this point. Then at 10 we will get this point, and at infinity we will having some point somewhere here. Now we will join all these points. So we are joining from here to here. So this is nothing but you can say the root locus. Okay. So root locus for unity feedback system GS equals to k by s. So here our arrows also indicate that root locus is moving, or roots are moving from s equals to 0 to s equals to minus infinity. Okay. So this is the simple problem. Now we will take another problem. Like consider GSHS equals to k times s plus 1 upon s time, obtain the nature of its root locus. Again we will write the characteristic equation, which is 1 plus GSHS equals to 0. So when we will do this, so you are getting this s plus 5 s times s plus 5 plus k times s plus 1 equals to 0, and it will become h square plus 5s plus ks plus k equals to 0, or h square plus s times k plus 5 plus k equals to 0. So now this is your quadratic equation. So in case of quadratic equation, we are having two roots, and we are finding the roots using the formula, Sridharacharya formula, which is s equals to minus b plus minus under root b square minus 4ac upon 2a. So by this we will find that the coefficient b is k plus 5, coefficient a is 1, and coefficient c is k. So it will become minus k plus 5 plus minus under root k plus 5 ka whole square minus 4k upon 4ab 4ac upon 2a. So 2. So when we have solved it, it is minus k plus 5 plus minus under root k square plus 6k plus 25 divided by 2. So you can see there are two roots. One is having with plus sign here, and another is having with negative sign here. Okay. So we have again made the table. Now this time we are having two roots rather than one. So this is the gain k, and this is the first root, and this is the second root. Now we will change the value of gain k again from 0 to infinity. So at gain k equals to 0, when you will put this value, you will find the value will become 0, and this value will become minus 5. Okay, and at k equals to 1, you are getting this value s1 equals to minus 0.1715, and s2 is minus 5.828. Similarly for 5 and up to so on infinity, we have find out these values. Now we are going to plot these values in S plane. So you can see this time there are two roots, so we will draw the movement of these two poles. Okay, so from here you can see, if you will see here, and here this is your open loop 0 at s equals to minus 1, and this is at s equals to 0, one pole, another pole is at s equals to minus 5. So when you will draw it, you are getting that at s equals to minus 1, 1 0 is there. So this is your 0, one is pole, another one is pole. Okay. So if you will see from here, we can observe number of branches are again 2. So when there are two roots which are moving, so we are having two branches, okay, corresponding to each and every root. Both branches are starting from s equals to 0 and s equals to minus 5. So one root will start from here, another root will start from here. But important is one of the branches terminate at s equals to -1. So this branch will terminate over here, and which is open loop 0, while other branch is terminating at infinity, like this. This is the portion where no root locus. No root locus means there will be no line here. Only this will be the root locus. While other branches terminating at infinity. It is very difficult to plot the root locus for higher order systems by the method of actually substituting different values of k in the roots of characteristic are used above. So it is important to note here that we have only taken the second order system, but when the system order is higher and number of poles and zeros will become higher, so there will be more branches, and in that case it is very difficult to plot the root locus based on this method. Okay, this is the traditional method. But what happened if the order is fifth order or sixth order? Then it is very difficult that we can solve it using this method, and then we can easily plot. Plot it. So rather than doing this, we are having certain rules. To simplify the construction of the root locus for higher order system, certain rules are specified based on the observation made earlier. So there are so many rules that we have to use to obtain the root locus for finding out the stability. Okay, so let us take another problem for GSH is equals to k upon s times s plus, and determine the coordinates of valid breakaway points. Okay, so breakaway point is an important concept while one of the important steps while for drawing the root locus. So first we will write the characteristic equation, which is 1 plus GSHS equals to 0, and we are getting this equation by solving s cube plus 5s square plus 4s plus k. Now we can write this equation like k equals to minus s cube minus 5s square minus 4s. Then we can take we will do the differentiation dk by ds. And then we will put it equal to 0, and the roots of this equation are nothing but the breakaway points. But as you can see, this equation is a quadratic equation, so we are having two breakaway points. But there is no guarantee that there will be two breakaway points or a single breakaway point or no breakaway point exists. Okay, so first we will obtain the roots of this quadratic equation. So after solving it, we are having two roots, that is minus 0.46 and minus 2.86. Now as we don't have we are not drawing the root locus, so we have to check whether both of these breakaway points are valid breakaway points or only one. So what we have to do for solving this? We will take the breakaway point, that value of s at which the gain k will become positive. So k should be positive for any of these s values. So we are putting it first for s equals to minus 0.46, we are getting k equals to 0.8793, which is positive, and for s equals to minus 2.86, we are getting k in k negative. So you can say this is the valid breakaway point and this is not the valid breakaway point. For the valid breakaway point, the gain k should be positive. So k equals to minus 0.46 is basically, you can say, is a valid breakaway point. So you can see here. Now another important thing is that this is the root locus we have drawn. Another important thing is that at breakaway point plus minus 180 degree by n, where n is the number of branches. So when two branches approaching each other and there will be a breakaway point, then it will be moved like this, plus minus 180 by n. So it will be separated at plus minus 90 degree. So here you can see the two branches are approaching with each other. That's why this angle is plus minus 90. And this s equals to minus 4, another root locus is there, and it is not there. Here there will be no root locus, and you are having this root locus which is terminating to infinity. Another is angle of departure at complex conjugate poles. So how you will calculate the angle of departure? Angle of departure is to be calculated in case of complex poles. How the complex poles will be terminated towards the infinity, that we can see using this angle of departure. Okay, So this is the equation given to us, and you can see there are 4 poles here because the equation is of 4th order, and zeros is only 1, z equals to 1. And poles, if you will solve, then you will find that poles are located 0, -4, -1, plus minus j. And 0, 1, 0 is located at s equals to -2. So how we will calculate? These two are complex conjugate with each other. So we will calculate only for one root, that is -1 plus j, and for -1 minus j, angle of departure will be the negative of that value. So -1 plus j, if you will see, this will located somewhere here, -1 plus j. Now what we will do for calculating angle of departure, what we have to do, we have to we have to check the angle that this particular pole is drawing from all other poles and zeros. So one pole is located at 0, so you can see 0. Another one is at -4, you can see this is at -4. One is here -1 plus j, and this is -1 minus j. So let us suppose this angle makes phi p1, this angle is phi p3, this is phi p2, this is phi z. So how we will calculate? So first of all, we will calculate the sigma phi p, which is phi p1 plus phi p2 plus phi p3. So you can check this angle is nothing but 180. Phi p1 is 180 minus tan inverse. This distance is 1. Tan inverse 1. It means tan inverse is 45. This is 135 degree. Phi p2, this angle is 90 degree. And phi p3, you know this distance is 3 and this is 1. So phi p3 is tan inverse 1 by 3. So tan inverse 1 by 3, it will become 18.43 degree. And phi z1, you know this distance is 1, this distance is 1. So phi z1 is nothing but 45 degree. Okay. So this angle phi is sigma phi p minus sigma phi z, which is 198.43 degree, and angle of departure is nothing but 180 minus phi. So you will calculate this angle is minus 18.43, and similarly for -1 minus j, the phase angle that you will obtain is nothing but 18.43 degree. Now we will see one complete problem. Okay. So sketch the root locus for the system having GS HS equals to K upon S times S square plus 2S plus 2. So first of all, we will find out the number of poles and zeros in this given equation. So let's say here you can see poles are 3, zeros there is no 0, Z equals to 0, and the number of branches of root locus is nothing but N or P, whichever is greater, or P or Z, whichever is greater. So here N equals, and here P is greater than P is greater than Z, so N equals to P equals to 3. So it means you can see it means what happened, it means there are 3 branches which will originate from open loop poles, and because there is no 0 for termination, then all these 3 branches will terminate over the infinity. And now we will see that which section of the root locus will lie on the real axis. So for that roots are 0 and -1 plus j, -1 minus j. So roots, one is here, one is here, one is here. Okay. So you can see so this portion, because right of this there will be no root locus, and here will be the root locus. Okay. And now we will calculate the angle of departure, which is nothing but calculated by angle of asymptotes, sorry, that is 2q plus 1 into 180 upon p minus z, where q equals to 0, 1, 2, which is 0 to p 0 to p minus z minus 1. Okay, so you will calculate the angle 60, 180 and 300. Then we will calculate the centroid, which is sigma real part of poles minus sigma real part of zeros upon p minus z. So this is value is minus 0.67. It is important to note that this centroid may or may not be the part of root locus. So here you can see the angle of asymptotes are 60, 180 and 300. So it means one branch is approaching to infinity along theta 2, while remaining 2 branches starting from -1 plus j will appear to infinity along theta 1 and theta t respectively. Now we will calculate the breakaway point. So breakaway points can be calculated 1 plus GSHS equals to 0. So while calculating, putting it equals to 0, so we are having breakaway point at minus 0.67 plus minus j 0.474 now. Now instead of for k, we can check validity of this breakaway by using angle condition. So actually what happened, whenever your breakaway points are complex, so it is difficult to find the validity of these points. So these validity of these points can be checked by the angle condition. You know, any point which is the part of root locus will satisfy the angle condition. So the point which satisfying angle is on the root locus, and point on the root locus satisfying dk by is nothing but breakaway point. So we will calculate the angle condition, angle of GSHS, which is plus minus 2q plus 1 into 180, and GSHS, you know this, put then s equals to minus 0.67 plus j 0.4714 in this equation, and we are getting this minus 164.11, which is not equal to minus 180 degree. So if the angle of this point will be equal to minus 180 degree, then only this point will lie on the root locus. So here this is not a valid breakaway point. So this is not multiple of 180, hence point is not on the root locus, and there is no breakaway point existing for this system. So there is no breakaway point. So when there is no breakaway point, then the situation will be like this. One root is at 0, one here, another one is here. So what happened? There will be no breakaway point, and this pole will terminate towards this left hand side and terminate to infinity, and another two poles will terminate to infinity. We will check. Now we will check the point at which this root locus will cut the imaginary axis. Okay, so again we will take the characteristic equation, apply the Rao-Hurwitz criterion over it. So after applying the Rao-Hurwitz criterion, we are getting the k marginal equals to plus 4. It means simply you can say that at gain k equals to 4, root locus will cut the imaginary axis. And auxiliary equation, this is auxiliary equation, which is 2s square plus 4 equals to 0. From here, the point we are getting at is plus minus j 1.414. Now because complex poles are there, so angle of departure will be there. So while calculating one, this is 135 degree, this is 90 degree, and there is no 0. So now we will subtract it, 180 minus 225, so minus 45 degree. So you can say minus 45 degree means somewhere here it will terminate. So it similarly for minus 1 minus g, it is plus 45 degree. Okay, so this is the complete root locus. What happened? This root will locate or move in this direction towards infinity, and another location is root is here. It will make minus 45 degree angle, and then come to in parallel with this asymptote, and similarly here it will become the, and this is the point we have, which we have calculated k marginal equal to 4 or s equals to j 1.414. And this is minus j 1.414. So if you want to comment on this stability, simply you can see as you are increasing the gain, this root is moving towards the left hand side, so it will not affect the stability. And but you can see these points as the gain is increasing, as soon as the gain k marginal equals to 4, your system will become marginally stable, and here system will become marginally stable, and the location or the coordinates of this point are s equals to j 1.414 and minus j 1.414, and then it will enter in the right half of h plane, so your system will become unstable. So you can say for k between 0 to 1 point between 0 to 4, system is stable. At k equals to 4, marginally stable, and k greater than 4, it will become unstable. Okay, so you can check here. Okay, so this is the similar problem. Here you can see there are 4 poles p equals to 4, there is no 0, so there will be 4 branches, and the starting points are 0, -2, -4, -8, because there are no zeros, so all the points will be terminated towards infinity. Now if you'll see the root locus point, so one is 0, -2, -4, -8, so you simply, root section of root locus will lie when only the number of poles and zeros towards a point should be odd. So here root locus will exist, because here you can see 2 points will be there, so no root locus. And here again you can see again there will be this point, so again this is odd, so this is the root locus section and this is the root locus section. And now we will check the angle of asymptotes. So we are having angle of 45, 135, 225, 315 and centroid at -3.5. Now we will check the breakaway points. So we are having 3 breakaway points. Now we will check the valid breakaway point. So when we will check the validity, we will found that -0.7585 and -6.652 will be the part of the root locus. So you can see, because -2 and -4, there will be no branch. So this, as you can say, not a valid breakaway point. And you can also find the value that by putting this value in the characteristic in the value of k, to find that whether, if the value of k is positive, then you can say for that particular root your gain is positive, so it is a valid breakaway point. Now we will apply the Rao theory. By applying the Rao theory, our aim is to find out the gain value at which it will cut the imaginary axis, and because there is no complex pole, so you can say there is no breakaway point required. So here is the root locus. You can see here, this is one root, another root is here, another root is here, another root is here, 0, -2, -4, -8. Okay, and what happened? One breakaway point here. So these two roots approaches each other, and at this point it will break down and they will move like this. And another root is here. What happened? It will start from here. It will start from here, and it will terminate like this, because this branch is approaching from here to here. So you can say one breakaway point is here, another breakaway point is here, and after this these points will be parallel to the asymptotes, you can say. So this is the required root locus, and you can see here the value of S is plus j2.138 and minus j2.138, at which it will cut the negative real axis. It will cut the imaginary axis. So system is stable at k marginal. We have calculated 235 points. So k 235.1 system is stable, and after it will become unstable. These are the references. Thank you so much.